Good morning, everybody, and thank you so much for joining this week's Planetary Sample Science Seminar Series. My name is Katie Goss, and I'm a PhD student at the University of New Mexico, and I'm really excited to introduce our speaker today, who is Dr. Mousumi Roy. She is a professor at the University of New Mexico in the Department of Physics and Astronomy. She received her bachelor's in physics from Stanford, her master's from Boston University, and her PhD from MIT. Her work right now is focused on modeling fluid and melt-rock interaction with a focus on the role of diffusion in trace element exchange. Her talk today is entitled Diffusion and Exchange-Driven Equilibration During Melt-Wallrock Interaction on the Moon. And whenever you are ready, please take it away.
Awesome. So my sound is
everything's there.
okay, great. So thanks everyone for coming, and thanks to those who are online for listening. So I'm excited to tell you a bit about the work that we've been doing in my group having to do with diffusion and exchange-driven sort of, I call it equilibration. It's basically irreversible processes that happen because of disequilibrium. And so before I start, I want to acknowledge my students, Colton Martin, and undergrads Braden Fields and Seth Medina, and also former student Kellen Malone, and then current collaborators, and also thanks to Chip for lots of great discussions. And the work was essentially, it's funded by NSF, but there was some undergrad support that we got from the Sustainable Space Research Grand Challenge at UNM thing. So thank you. All right, let's get started. So I divided the talk. Let's see. So
Yeah, 5 seconds left.
okay, there's a lag. All right, I divided the talk into 3 parts. So I'm going to start with talking about ideas for melt-rock interaction and its role in the creep signature in the lunar crust. And then talk about melt-rock interaction and consequences of disequilibrium in the work that we've been doing in terrestrial settings. And so using that, starting with that, we're going to use that as inspiration to build some models and frame some hypotheses about thermal disequilibrium and chemical and isotopic disequilibrium. And I'll close the loop and come back and talk a bit about creep. So I'm going to start with the first of these boxes. So ideas for melt-rock interaction on the moon. So as you all probably know, that the creep signature, the enrichment in potassium, phosphorus, rare earth elements, associated also with uranium and thorium enrichment. Let's see, I will try, is that a laser pointer that I can use or not really? Okay, so let's see, if I do this, I don't like that thing at the bottom. Do you see that thing at the bottom?
Yeah.
Yeah. All right, well, I guess, okay, so this is the so-called Procellarium creep terrain, and on an iron map, it shows up as this very red region, and it sticks out also from the point of view of its thorium content. And this is where the creep signature, the sort of geochemical signature associated with rocks in the PKT are found. And the signature is not only limited to the PKT, but it's most commonly associated with it, obviously. And it was recognized in sort of lunar soils way back in the beginning, in the 1970s. And since then, this has been a geochemical kind of characteristic of certain materials on the lunar surface. So in basalts, creep basalts, the signature looks like rare earth element enrichment, and it's, if you normalize by chondrite, it's on the order of several hundred to nearly 500 times more enriched in the light rare earth elements. It's associated with this negative erodium anomaly. It's probably then associated with melting of material that is an isotopically enriched source, probably a complement to the northicide crust, which has a positive erodium anomaly. There are some really important features in the major element chemistry, like slightly more aluminum content than most Murray basalts. And importantly, the creep Apollo 15 or the creep basalt signature is associated with an isotopically enriched source compared to the rest of the Murray basalts. So the question that we'll be focusing on today in this talk is, can you make this kind of material, starting with a high sort of magnesium content parental melt, but then assimilating the creep signature by melt-rock interaction? So that's sort of the thing that inspired us to apply the diffusion models to this setting. We're in the beginning of that process, and I'll talk about what I want to do to sort of explore this possible question on the moon. Similarly, the magnesium sweet rocks. So in some of them, you also see a creep signature. This is a generally lower abundances of rare earth elements than in the creep basalts. Again, this suggests a high magnesium number source for the parental melt, which then possibly could have assimilated the creep signature by, interacting with some plagioclase-bearing cumulate that's more evolved, and plus or minus a creep-rich horizon or a creep-rich layer. So in all of these cases, if this is going to work, if you're going to do this assimilation using assimilation to get the creep signature, you have to start with some hypothetical ore creep idea, where as a result of the kind of last stages of crystallization of the lunar magma ocean, you would have formed an incompatible element enriched residuum, something that has to look like it's depleted in both nickel and cobalt. And people have looked at things like what the possible model ages could be for this thing, for this material. But importantly, because it's associated with the last stages of the LMO, it is, kind of most likely buoyantly situated sort of just below the crust mantle boundary. So some of you probably know about the idea of cumulate mantle overturn, where also in the final 10% of lunar mantle lunar magma ocean crystallization, you get these ilmenite-bearing dense cumulates. And the idea of cumulate mantle overturn is that those dense cumulates, because they're gravitationally unstable, would essentially sink down into the rest of the LMO, and that can drive upward motion in response of really magnesium-rich cumulates that are earlier crystallizing materials. What that does is gives you a way to drive decompression melting in the lunar magma ocean in response to this overturn. That decompression melting is then a source for these parental magmas, which then eventually interact with the creep horizon. Now, there are also, this idea has been around for a while, and I'm going to talk a bit about what this means for melt-rock interaction and the consequences of disequilibrium between melt and wall rock. So this is a classic picture from a paper by Dolph et al., where this is a cartoon of the PKT terrain, and they're looking at a cross-section that looks at the crust, roughly 60 kilometers thick or so, and then the uppermost mantle. And So the idea here, and I've highlighted it in pink, you'll see it'll be a theme throughout the talk. So things in pink will have to do with, this ore creep horizon, right? And this ore creep layer then is a place that, it's hard to imagine that it would be involved with the ilmenite-bearing cumulates and sink down, but it's possible that some of it could be also dragged down. But the idea is that its buoyancy holds it up against the crust mantle boundary. So that then says, well, okay, if we're going to assimilate this creep signature and produce creepy materials on the moon by magmatism, then in these yellow areas here, here, and here, I've kind of highlighted places where, you could get interaction between parental magmas from deeper within the moon interacting with some kind of an ore creep layer. The thing that's going to be really important in everything I'm going to tell you about is the idea of coupled thermal and chemical disequilibrium. So at each of these locations, for example, right here, if you had sort of a picritic, deep-seated melt source that was driving magmatism, and those melts were rising to form, say, Mare basalts at the surface, you might have places where essentially they're interacting with wall rock, shown here in this cartoon, that is essentially this ore creep, right? So when I draw these cartoons from here on out, each one of these things that I'm calling a channel, well, think of it as a melt-rich region. It's not pure liquid material, but it's a higher porosity than the general, right? And in the real world, there's probably a gradation across that boundary, but the wall rock then is melt-poor. So it's lower porosity than the channel. So this idea also works for the genesis of, say, like the creep and magnesium sweet rocks. So you might have melting of, cumulates that are magnesium rich, and you could physically mix them with some ore creep and plage-bearing anorthosite crust, and then produce melts of those that then lead to the magnesium sweet plutons. In each of these cases, you would have Melt-Wallrock interaction with these creep-bearing layers. This is a recent, so this is a paper that came out fairly recently, and there's some things about this cartoon of the lunar sort of mantle, cumulate mantle overturn, where in the black areas, you've got ilmenite-bearing cumulates that are sinking down into the deeper mantle, and in yellow is this ore creep, region. And these people argue that some of it might actually be dragged down. The feasibility of that dynamically is something that still needs to be worked out. But what they also point out is that, when you have magnesium sweet magmatism at the crust mantle boundary, it's Melt-Wallrock interaction, driven again by thermal and chemical disequilibrium, that would give rise to the signatures of, say, the pink spinel troctolites that show you that you had some sort of assimilation with the northicitic crust. So, even more recent work, so looking at the entire magma ocean as not literally, just a cumulative pile, but rather a compacting mush with crystals, also gives you a possible way of generating parental melts, which then would interact with the ore creep that I've added, modified from these guys' cartoon here. But the idea then is that it's after the interaction with the ore creep, or in that sort of region of the ore creep layer, where you would have sort of channelized flow. Now, this is no longer compaction driven, it's pressure driven probably, but channelized flow where the melt is focused into high porosity regions and there's wall rock interaction as the melt moves through. So it's, again, a channelized setting where you can have disequilibrium. The thing about porous flow, and particularly at the grain scale, if you have porous flow, is that you're likely to reach thermal and thermodynamic equilibrium much more quickly than if you were moving quickly through a channel. And that's contained in this thing called the Peckley number. And the Peckley number that I'm thinking of for these channels is much, much higher than that. That would characterize, let's say, the deeper part of the lunar magma fissure. All right, so with that as a kind of lens to frame our hypotheses, now let's go to what the models tell us about melt-wallrock interaction. And I'm going to start with some inspiration that originally made me think about this, and that is, we were looking at the feasibility of melt-wallrock equilibration in the transport of rare earth elements, particularly neodymium isotopes. And this was driven by some work I did with Lang Farmer at CU Boulder and former student Helen Malone. So the idea now will be that we're going to have a melt-rich channel, and we're going to just confine our attention to 4 processes. So within each of the wall rock, let's say right here, and within the melt-rich channel, you will have diffusion-driven equilibration. So if there are gradients in concentration, they will, sort of diffusively relax. Number 4 is a process that's advection. So the material in the channel is moving relative to the wall rock. All of the model is in a reference frame that's stationary with respect to the wall rock. And then number 2 is really the most important part. 2 is the assimilation. And here we're going to think about that as diffusion and reaction driven. So you could have dissolution precipitation reactions and also diffusion of trace elements. And we were inspired by this when we were compiling some work, some data on Cenozoic basalts in the Western US. You may know that the Western US has undergone a really profound transition from subduction in Mesozoic time to sort of extension in the latest Cenozoic. And we were looking specifically at tantalum over thorium ratios. And, low values are correlated with flux melting, and high values, high tantalum over thorium is generally associated with decompression melting. So in the Western US, we see this really nice transition temporarily in many places from low tantalum over thorium to high tantalum over thorium. What was intriguing to us, though, is that if you look at the low tantalum over thorium group right here, those and I should say, all of the data shown here are for primitive basalts that are MgO weight percent greater than 6. So we're trying to, look through any kind of crustal processes. And what you find is that with the low tantalum over thorium, the so-called subduction-related flux melting rocks, when they are erupted through thick lithosphere that's Precambrian, like Archean age and Proterozoic age, their epsilon neodymium value is more negative than it should be. And it looks like the lithosphere that it's going through. And so that was our inspiration. I kind of said to Lang that this is a very sort of sacred thing, right? We assume that the neodymium isotopic composition of a primitive melt ought to reflect that of its source. But this smells like transport. How much could transport play a role? So that was the inspiration. So we're going to start by looking at things on the left. These are dumite channels. and from an ophiolitic setting, or you could go to the Laird's Massif in Europe, and in that sort of setting, and you can come up with, the kind of metasomatic reactions, for example, in the Laird's Massif, the refertilization of Harzbergite to make lairzolite is actually what is the lairzolite in the Laird's Massif. This, what was thought to be pristine subcontinental lithospheric mantle, is actually melt refertilized, right? But the spacing between the Harzbergitic regions and the lairzolite then gives you a sense of these melt-rich channels, right? This gives you a sense of the scale over which you are having fluid transported. In addition, we got inspiration from the Ronda peridotite massif, and I have some pictures that I'm not going to have time to show, but that also tells you that you have very big sort of transient geothermal gradients that people have recorded by very painstaking fieldwork. That looks like, 230 degrees C per kilometer of temperature gradient. So this is where those melt channels are found, and in peridotic settings in the mantle lithosphere. And if you think about, just like in the moon, right, the boundary there is the crust mantle boundary that we're thinking about. But the most important thing is that it's a permeability contrast, just like the lithosphere stem sphere boundary here. So once you're in the lithosphere, in the cooler part, you were being transported in channels. And so the channel spacing and the kind of gradients that we needed are inspired by these geologic observations. The next slide is the only one with equations. So it didn't, oh, there we go. We're going to start with just building the feasibility argument. And this was from a paper that came out last year in GQ. And it built the feasibility argument using a 1D calculation. It basically parameterized this entire channel transport network into 3 important variables. So if I go back to this, the 3 important variables are the melt-rich channel volume fraction, the channel spacing, and the relative speed. To start with, that's what we kind of built the model around. But the most important part of it is that it's an advection, diffusion plus exchange, linear exchange. And what I mean by that is that there's for example, if you're in the channel, I call that a fluid, you have the typical advection term, and then you have a diffusion term, and then you have a term that I'm calling exchange. And the box in these equations can be whatever concentration of, say, neodymium or lanthanum or cerium, right? Or an isotope of neodymium. And the equilibration here is driven by this exchange term, which depends on how far you are from thermodynamic equilibrium. So that's why I call it a linear exchange, because the larger the difference between, say, some partition coefficient times the concentration of the fluid minus the concentration of the solid, that term, the bigger it is, the farther you are from thermodynamic equilibrium. All right, so now the exchange term, it turns out, is, I'm going to get rid of this thing. I don't quite know how to do that. Keep it permanently gone. But the exchange term depends on a time scale. And this is where the physics comes in. The exchange time scale, think of it this way. It's basically, there are 2 ways to think of it. I think the more physical way is the exchange time scale. But the way I've written it is 1 over that time scale. And it depends on 2 terms in this calculation. It depends on the diffusivity, right? How quickly things diffuse between the melt and the wall rock. And the rate limiting diffusivity there is whatever the wall rock is. It's very slow compared to the melt. The other term is what I call a reactive term. R is a linear reaction rate, like if you're having dissolution precipitation in like 10 to the 13 meters per second or so. Roughly, that's the rate at which crystals dissolve and precipitate. All right, so that gives you a time scale. That time scale, if you compare that to the rate at which advection is happening, or the time scale of advection, you get what's called the Dunn-Kohler number. And that's just a ratio of two time scales. And the key to the Dunn-Kohler number is that the higher it is, for example, the shorter the exchange time scale, right? Then the higher the Dunn-Kohler number, the more equilibration you get in a given amount of relative motion. Got it? All right. So this is the equation. This is the set of equations that we solve for various neodymium isotopes. And the most important thing in this paper, in the GQ paper, is the argument that yes, there are lots of experimental constraints on the diffusivity of neodymium in olivine and OPX and CPX, et cetera. But what's important is not the individual lattice diffusivities, but rather the diffusivity or the effective diffusivity in a wall rock that's a polycrystalline aggregate. So you have grain boundaries, which already are seats of disorder, and they have, sort of higher strain energy associated with them. And trace elements, and petrologists have known this for a while. So can I do something? Oops. Okay, let's do this again. Okay, so petrologists have known this, that trace elements and incompatible elements that are trace elements will tend to sort of go into the grain boundaries, and that there are two effects here. One is essentially a segregation effect, that the grain boundaries segregate these trace elements by a factor 10 to the 4 in these calculations, but it depends on the grain size. There's also an effect of anisotropy. And what I mean by this is that if I had, this is a peridotite thin section, and we just digitized it and just ran a diffusion calculation with, some diffusant starting at the top and diffusing down into the material. And you can see that over time, right, the grain boundaries are acting like superhighways. So I can then take an average across here and plot the concentration, average concentration, as a function of depth in the wall rock, fit an error function to it, and that gives you an effective diffusivity. That effective diffusivity turns out to be much higher than the lattice value. It depends on a couple of things. It depends on what you're assuming for the segregation, but it also depends on the grain size, because it depends on the geometry of these superhighways, right? So this is a calculation that looks at that effective diffusivity. So this is the effective diffusivity divided by the lattice value, and it's done for decreasing grain size. Think of it that way on the x-axis. And so what you can see is that the enhancement in effective diffusivity, depending for different wall rock domains, different grain sizes, et cetera, can go up an asymptote up to our assumed value of the grain boundaries being 10,000 times faster than the lattice value. Right, so you can get this enhancement, and that's really important. What that does is that it basically means that if I had a melt-Wallrock interaction in a system, this is still just the 1D calculation, right? And imagine that I had a melt coming in over here, a fluid parcel entering at this end with, say, epsilon +8. Right? And then the adjacent wall rock that it's entering into starts off at -2, just for argument's sake. What I'm asking here is, under what circumstances, after 10 kilometers of transport, do I get those two equilibrating? Can I shift the epsilon neodymium value of both the wall rock and the melt? So I'm going to codify that with this quantity called delta 10. Delta 10 is just 1 minus, this amplitude divided by that one, okay? So if delta 10 is 0, right, then these two are the same, and therefore you have no equilibration. So that's what's being shown over here. You would have that when there's very, very little exchange, when the exchange timescale is very long compared to the advective one. That's when the Dunn-Kruger number is small. Delta 10 would be larger than 0, and that would indicate partial equilibration here, and that will happen when you have sufficient exchange such that the fluid and the solid are approaching each other in their, after some amount of transport. This could be delta 20, delta 30, it doesn't matter. The reason it's delta 10 is because this is a 1D calculation, and it's only to give us a flavor of what can happen. It's not meant for transport across the entire lithosphere, right? So I'm just using it as a feasibility calculation. The assumptions that go into this are that you have some constant average values for each of these calculations, for the relative Wallrock and melt motion, V, the channel spacing, and the channel volume fraction. And it's by changing these three that I can go from delta 10, 0 to delta 10, say, greater than 0. Okay, so that's sort of shown here in this diagram. The idea is that delta 10, I've drawn it like a phase diagram here, where the Dunn-Kruger number is down here on the x-axis. The y-axis is kind of like I have a time scale over which the melt is being perturbed inside the channel. So at time t equals 0, the melt comes in with that +8 relative to the solid, right? And this red region is the region of partial equilibration. And to get partial equilibration, basically you need Dunn-Kruger numbers for a whole range of timescales. You need Dunn-Kruger numbers larger than about 10, right? So the question is, how do you get there? So on the right-hand side, I show you essentially, just focus on this star, which I've highlighted here. This is one set of parameters where the Dunn-Kruger number is 10. The channel volume fraction is about 10%. Channel spacing is about 1 meter. Rate of ascent is about 1 meter per year. But if you change those things, you get these contours of Dunn-Kruger number, right? And if you change on the y-axis, this is the reaction rate, the dissolution precipitation rate. That's also leading to this exchange. There are two parts to it. There's diffusion and reactive assimilation. So the point of this star here is to show that you can get Dunn-Kruger numbers larger than 10 to give you a delta 10 that is appreciable, positive delta 10. That means that you're getting partial equilibration for a really feasible set of parameters. So we should be careful. That means that your isotopic composition is changing as the melt moves in the Wallrock. All right. So now I'm going to just quickly give you a run through of some new work. Those were 1D calculations. This is new work done by Colton, who's here, and a couple of undergrads. We started off just looking at 2D models of coupled thermal and chemical disequilibrium. So imagine that I have a Wallrock domain like this. I have a melt channel inside which stuff is moving. And I'm going to perturb material coming in just right here in the inlet of the channel. And the perturbation will be both in temperature, and it could also be in things like epsilon neodymium or the concentration of lanthanum, whatever you like, right? We're going to assume that here we assume something like 1,000 Kelvin, an initial state of equilibrium. We're doing, the next calculation is just for neodymium. So here's the partitioning that we're assuming for neodymium. And to be simple about it, to start with, the entire Wallrock is just CPX, okay? So just bear with me for a minute, because I want to show you this is how you build intuition, and then you get to more complicated settings that are more realistic, right? Okay, so I'm going to assume the same thing. My grain boundaries are faster than the lattice by factor 10,000. By the way, there are some heterologic arguments that that factor could be as large as 10 to the 8, 10 to the 9 in some cases. We're being conservative here. And this is the lattice value, 10 to the minus 18, and the melt value is 10 to the minus 11. All right, so what happens when you have a perturbation that looks like this kind of step function wave? So now I'm gonna, let's see if this will work. It should work. So what I've done here is I'm playing a movie just to build intuition, where the step function is happening in the channel, and you can kind of see the sort of moving down and sucking back out of these trace elements, right? In this case, neodymium. Here we have a periodicity of about 160 years. And on the left-hand side, this is what I call an apparent partition coefficient. The red line is the initial state. Please play. Okay, the red line is the initial state, which is thermodynamic equilibrium. And right near the Wallrock is a place where you have apparent partition coefficients that are away from equilibrium, right? So this is what we call a melt-rock interaction zone. It's the zone of chemical disequilibrium. So if you were to take a piece of this Wallrock, if you were far enough away, you would essentially be sensing only thermodynamic equilibrium. It's only when you're close enough within this delta width that you can sense this disequilibrium. All right, so to apply this idea, we then started a collaboration with a whole bunch of people looking at oceanic peridotites from a place called St. Paul's Rocks. St. Paul's Rocks is out in the middle of the Atlantic Ocean. It's on a transform, and this is work that's collaborative with Frieder Klein, Tim Schrader, Jessica Warren, and Emmanuel Cadillo. So these samples were either dredged or rover samples, and they also include a lava sample, an alkali basalt that was erupted nearby. So this is what the data looks like, and this is why we got so intrigued. The data, let's first look at this picture right here. So on the left, this is the sample composition for these seven trace elements as a function of MgO over SiO2. And the peridotite samples all lie in this gray field. The symbols are the samples for which we have modal mineralogy. So that was not measured for every single sample, all right? What's shown on the y-axis is normalized by the composition of an alkali basalt that erupted nearby. So what you see is that all of the peridotites show, essentially, they lie in a compositional array that points to the alkali basalt. And as a function of MgO over SiO2 decreasing, so getting more evolved, you're approaching the alkali basalt, right? And this is another way to look at it, the same trace elements, and the y-axis is the same on this one. And here, this is a view of the exact same data. There are two different data sets in red and blue, but the darker the color, the more pristine or the higher the MgO over SiO2, the lighter the color, the more evolved. And you can see that the black here is the lava, and all of these approach the lava spider diagram as you decrease MgO over SiO2. So what this looks like to a petrologist would be, quote, melt addition, right? So you can say, oh, these form kind of a mixing between some pristine composition and the composition of the melt. What we wanted to do is try to understand, what does that actually mean, right? Can you achieve this with a diffusive process? And I'm going to not include reaction right now, just diffusion, just to get a handle on it, an end member handle on it. See, when you say melt addition, to someone who's thinking about the physical processes, like, how do you get a sample that's low in NGO over SiO2, it has more amphibole, that's one thing, and it's approaching the alkali basalt, then you say, well, are we actually mixing the melt at the fine grain scale? That could be one possibility. So you take a whole rock sample and you crush it, and you're just picking up more of the melt that's in between the grains. So we decided, look, this is off axis at a mid-ocean ridge. You have metasomatic fluids that may be entering into the lower lithosphere. Those fluids could be interacting with the wall rock, and maybe diffusion alone could give you this cryptic metasomatism and modal metasomatism because of water in those fluids, right? There could be phase changes. We're going to ignore all that. But the point is that we'd like to try to understand what that array, what physically is causing that compositional array. So Colton took the same kind of calculation, but now we have, instead of a step function that's oscillating, just a simple, kind of step function, a pulse, if you will, of material that's initially, you have in thermochemical equilibrium, and then you have a pulse of disequilibrium. Here, the diffusivities that we used are Arrhenius functions, so temperature and pressure. And he did this not just for neodymium, but a whole bunch of those 7 trace elements. Because we're in an oceanic setting, we start with an initial state at about 800 C, 1.4 GPa, like about 50 kilometers below the seafloor. All right. So the basic thing, so this is a calculation using a finite element mesh. That gives you an idea of what the mesh looks like. The basic thing you find is that if black here on the left represents an initial thermodynamic equilibrium, when you see colors that are lighting up, that means that the disequilibrium front is moving through, right? So at early times, you have a small region of the wall rock that is sensing that pulse. At later times, you have a much deeper region into which you're communicating, all right? So at early times, for example, this is up against the channel, material is kind of, the grains that are right up against the channel have reached their saturated in their partitioning. It's only those ones a little deeper below that have quarter rim gradients, and you're beginning to see that flux inside into the grain. And then over time, the material right up against the channel just looks like, the neodymium or lanthanum or whatever trace element is just moving right through. This is just like your, champagne tower, right, in a wedding where the upper glasses are full. All right. So we then took the average wall rock composition and calculated that through time. So this is time here, and this is the wall rock composition normalized by the melt value. And you can see that initially, right, there's a very fast transient, and then you kind of saturate out into whatever your composition is going to be. In this case, right, we're getting to about 30% of the melt value. We're not reaching the actual lava value. Okay, so then Colton calculated spider diagrams through time. So that's the next obvious thing to do. You start with some composition that's initially down here. Here's the alkali basalt value, and these kind of multiple dashed lines here are the compositions through time. And what you can do then is say, oh, so now I can ask the question, how long does it take? How long does it take for me to get to the observed compositions via diffusive equilibration? That depends, of course, on the NGO over SiO2. One thing I forgot to tell you is that unlike the first calculation I showed you, these calculations with all the different colored grains here, these have the mineralogy that was measured for a given sample. So those calculations are sample specific. What's being assumed here now, I know it's a bit odd to say, oh, I have some fraction amphibole, I'm going to just put that in my Wallrock. But what's being assumed here is that if you have modal metasomatism and you're growing amphibole, that's going to be rate limited by the diffusivity of water. And the diffusivity of water is much faster, higher than the diffusivity of trace elements. So we're taking an extreme view and we're saying, okay, metasomatize modally, give me the modal composition, tell me what the diffusion does for the trace elements, all right? So anyway, to summarize, these models kind of show you that this so-called melt addition, right? For the end member process of diffusive interaction, you could model that as a physical process of trace element exchange. These observable kind of rare earth element enrichments in these calculations are achieved over timescales that are reasonable for the oceanic setting. In the future, it would be good to include things like phase changes and reactions. And certainly from really detailed studies of the nature of where trace elements are stored, like in particular, I'm thinking about the atomic force microscopy work that is in this paper. I mean, what you call a grain boundary depends on the trace element, right? So we have to be careful about that. That isn't taken into account. So I'm going to spend a few minutes just closing the loop here and coming back to the lunar setting and the ideas for creep. So what can we do in the lunar setting with these models? So one thing is that to think about is that this exchange timescale, it depends on things like, well, what trace element are you interested in, right? So and the Dom color number is element specific because it depends on the diffusivities and things like this. Magma ascent rates, I think we have reasonable handle on at least the last part of the ascent process. For example, constraints from picritic glasses more recently. So what we could do is use these models to come up with, hey, what time scale of melt interaction, melt-Wallrock interaction would you need to actually produce a certain creep signature? So in addition, this is another way of thinking about enigmatic observations like these Chungi 5 basalts, where people have argued that they don't have all of the sort of, they come from a more isotopically depleted source, yet they have, not quite creep level values, but lower signatures. So perhaps there's a variability in melt-rock interaction and a diversity of creep-like lithologies that we could try to address using assimilation models like this. Okay, so in conclusion, I would say that I think it might be really fruitful to think back to the idea of metasomatism and creep as related to Melt-Wallrock rare earth element equilibration. And the most important thing is wherever you have thermal and chemical disequilibrium, and that's most likely to be where you have channelized transport. Right, so this could be really important, for example, in the genesis of the magnesium suite or creep basalts. So here, for example, in this cartoon, you have, channels that are rare earth element poor entering into a Wallrock that is more rich in rare earth elements and emerging as rare earth element enriched. But on the other hand, the other possible thing you could think about if you're thinking about disequilibrium is the opposite process. So you could have a crystal setting where you have channels that are, let's go back. Channels that are rich, that are rare earth element rich, so the melt that is interacting with, say, the wall rock, which is crustal northicide, rare earth element poor, and then leaving a creepy signature in the crust. So anyway, those are some ideas to think about, and I will end here and see if there are any questions.
Thank you so much, Mousumi. That was a really great presentation. So yes, we will open it up to questions now. So you can put your questions in the chat. You can raise your hand if you're online, or if you're in the room, you can also ask questions.
So do you want me to just pick people and someone's monitoring the chat?
Yes,
Okay.
I will monitor online. So if there are questions in the room, there's nothing online right now.
Okay, go ahead.
That was a wonderful talk. I loved it, and I think this is really elevating the conversation about how to think about this. I've been fascinated about this idea of how commodity item melts have really high assimilation capacities. And this idea is really interesting. I haven't thought about the saturation state of rare elements, but I assume in most melts, they're almost never saturated.
Right.
They're always undersaturated. So I'm thinking about how this might be a good explanation for decoupling major and trace elements, because they're easily saturated and could precipitate, the rare earths cannot. So this process, does it just slow down as the concentration gradient decreases?
Yes, that's right. So, I mean, look, we're using the diffusion equation. When you do that, it's a representation of something that's an irreversible process that already you're assuming like some PDE is a good representation. But yes, it's true that if you have gradients that are decreasing and the flux depends on these gradients, you will equilibrate more slowly. And actually that's what that's really the reason for this kind of slowdown in the rate at which the concentrations are increasing. But this idea and these models were designed for trying to understand cryptic metasomatism. And so, yes, that decoupling of major elements and trace elements.
Wonderful.
Anything online?
There's nothing online at the moment.
Okay. Go ahead, Chip.
Chip, I've got a question. During this process, what sort of heat is being lost by the fluid or the melt in the channels?
Yes.
Because obviously when you have what people consider assimilation, very commonly you have a lot of heat loss to assimilate this material, therefore causing crystallization of other phases.
Yes.
Have you pondered what the heat loss could be and how similar it is or different it is from assimilation?
Yes. So I didn't have a chance to talk about it here, but I had a paper in 22 that looked at just thermal disequilibrium.
Mm-hmm.
And what we're showing now with that same model, it's a 1D model, but we're trying to look at melting of the wall rock in response to heating by channelized melt flow.
Mm-hmm.
And at the same time, crystallization of the melt in the channels as a result of cooling by interaction with the wall rock. So none of those phase changes are here in this calculations that I showed you. But that is something we need to include in the 2D calculations. We've started doing that in 1D. But what we're finding for the Western US setting, for example, for those 1D calculations, we're actually able to think about the seismic signature of the lithosphere-stenosphere boundary. In some places, it's very, very sharp. In other places, it's much more kind of a gentle seismic velocity gradient. And we're able to think about interpreting those differences, say in the Basin and Range and the Colorado Plateau, in terms of wall rock melting. So what we're finding is that it's not, you can change the channel volume fraction by quite a bit if you have thermal disequilibrium. Here in these calculations, the temperature change, the delta T that was applied at the same time, coeval with the concentration change or the concentration pulse, was something on the order of 400 Kelvin. And what that does in these calculations is that it immediately, because heat diffuses so quickly, it immediately makes the diffusivity in the wall rock much higher because of the Arrhenius factor. But there are no phase changes yet. So that's something we have to put in.
There is a question in the chat from Thea McKenna who asks, how does the theory of creep depleted melt channeling through creep wall rock work with the subcrystal creep model you had in the introduction?
Subcrustal creep model. Oh, okay. So the thing that I was talking about way back when I started thinking about kind of creep related interactions in, I think you're talking about edges of magnesium sweet intrusives and things like this. So the idea is that if I can jump to the final slide really quickly, it's shown in cartoon form. And the idea is that if you have rare earth element signature that's enriched inside the melt channels, and you're walking or you're transporting into a wall rock, say the crustal northosites, that might start off being rare earth element poor. As melt-Wallrock interaction happens, you could actually re-equilibrate so that you could give some of the creepy signature, the rare earth element enriched signature, especially the light rare earth element enrichment, into the crustal material of the wall rock. So that's what I tried to sort of show in cartoon form here. Nothing in the model. So I should make it clear. I mean, yes, we're using the diffusion equation, and nothing in the model is specific to a particular direction of exchange. It's the degree of thermal and chemical disequilibrium that drives the direction of exchange. So that's all you need.
It looks like they're saying, sorry, I meant the left panel on that slide and how that works with models that have a layer of creep underneath the crust after crystallization.
So the wall rock, oh, so are you thinking of the layer of creep being sort of partially crystallized or not crystallized at all? Because the way this is being, what I'm thinking of is that you basically have a layer which is, it could be a mush, but it's mostly mostly crystalline, and the melt is higher porosity channels. So the channelization puts relative motion between the melt in the channels and the mostly crystalline wall rock. It could have some porosity on the outside in the wall rock, but that's it doesn't have to be fully crystalline, if I understand your question correctly.
Well, are there any other questions in the room? There's nothing else on the chat at the moment, and I know we are at time.
Last question in the chat.
Oh, yes. Wenba Zhang says, a follow-up question about creep. Since creep is considered to be enriched in heat-producing elements, how would creep affect the melt-rock interaction in terms of thermal effect? Like, what if creep is wall rock?
Yeah, so that's a good question. So right now in these calculations, for example, the results that I showed you for the peridotite here, in these kinds of calculations, what's being done is you're providing a perturbation both in temperature and in concentration. That's a finite pulse. What I imagine is that if you had a wall rock, let's say that's enhanced in uranium and thorium, you might have an initial thermal gradient. And so that's just a background state. That thermal gradient, though, is not going to be important over the length scales of, few centimeters around the channel. That's the sort of length scale of these kinds of models. Those thermal gradients would be important over the kilometer scale. So that's a bit of a, there's a bit of a disconnect between thermal gradients and chemical gradients for this reason. And actually, that's the reason why we started off looking at 10 kilometers of transport, but now, because we want to look at grain scale processes, we focus down to centimeter scale models.
Sweet. Well, thank you so much again, Mousumi, for giving the talk today. And yeah, another round of applause. And I'd just like to remind everyone that next week, Scott Eckley will be giving a talk about the utilization of X-ray computed tomography during the preliminary examination of unopened Apollo drive tube samples. So hope to see you all here next week and hope you guys have a good rest of your week.